use to figure out which kind of frequencies it tends to grab for itself. Okay, phase is one value at this one frequency of the circuit. Okay, we look at the formula for the impedance. What's the formula for the impedance of a resistor? R, no information. So you're about to offer an answer or ask the question. Okay. Yes. If you have, I agreed with your whole sentence until the last part. Yes. Okay. Yes. Okay. Whichever circuit element has the largest impedance gets the largest voltage. Because V equals IZ, correct? So if you look at all these V equals IZ equations, since these circuit elements are all in series, they've all got the same I. Agreed? So given that they've all got the same I, the one with the bigger Z gets the bigger voltage. Has everybody agreed with that? Now, resistors Z, the Z of the resistor in this circuit is 120 ohms, period. What if I doubled the frequency in the circuit? What's the Z of the resistance? Still 120. What if I quadruple the frequency in this circuit? What's the impedance of the resistor? 120 ohms. No matter what I do to the frequency, the resistor is always 120 ohms. However, the formula for the impedance of a capacitor which I just erased in order to make room to write it down. Okay? You're getting punchy already. The Z of a capacitor is 1 over omega C e to the I minus 90 degrees. The minus 90 degrees means, in this case, current first, then voltage, because that's what we understand about how capacitors function. And the number in ohms is this one, 1 over omega C. What happens if I double the frequency? You half the number of ohms. If I quadruple the frequency, quarter the number of ohms. If I make the frequency tends towards infinity, what happens to the resistance of the capacitor? Goes to nothing, and it takes none of the voltage. So who gets the voltage? The resistor. So at high frequencies, the resistor gets it all. And at low frequencies, if I have the frequency, I double the impedance. And if I take the frequency to 0, so that omega, which is 2 pi frequency, goes to 0, what do I get for the impedance of the capacitor? Infinity. So I've now got 120 ohms from that resistor in competition with infinity. Who wins? Infinity. So at the low frequencies, the capacitor takes it all. At the high frequencies, the resistor takes it all. Because the resistor's role in any circuit is leftovers. Because it has an impedance that doesn't depend upon frequency. So whatever the capacitor doesn't take for itself, or if this were an RL, whatever the inductor doesn't take for itself, or if this is an RLC, whatever the L and C don't take for themselves, the resistor simply mops up the leftovers. So in a capacitor circuit, capacitor grabs low frequencies for itself. Because its frequency goes to 0, the Z of the capacitor goes to infinity. And so if you wire another circuit in parallel with the capacitors, that circuit also gets only the low frequencies. If you wire another circuit in parallel with the resistor, that circuit gets the high frequencies. So let's read the questions and see if we can take the language of the question and map it onto our understanding. If the voltage across the capacitor is used to power another circuit, would this system be considered a high pass or a low pass filter? Low pass. because that other circuit gets the same as the capacitor in parallel with the capacitor, and those are the low frequencies. If the voltage across the resistor is used to power another circuit, would this system consider to be a high-pass or a low-pass filter? High-pass filter, because the capacitor takes all the low and the resistor takes the leftovers. Okay? Now, finally, oh, I didn't realize I threw this question in so early. Okay? You become bored with this circuit already. I thought we'd have to go through several of these until you were completely bored, but apparently, according to this, you're already bored, and you're bored with this circuit, and you decide to change it into a radio tuner designed to tune this same frequency. What would you add to this circuit? This circuit is now a filter. Everyone agrees? It's a low-pass filter if you take in parallel with the capacitor. It's a high-pass filter if you take in parallel with the resistor. This is a filter circuit. We want to make a different circuit. We want to make a tuner circuit. RC, no matter what the R and what the C is, will never be a tuner circuit. So this question asks, what circuit element would you add into the circuit to make instead a radio tuner? What would you add? An inductor. Very quickly, we'll do this in more detail later. Can everybody get there in their head? It's a series circuit with an R, an L, and a C. And then the L comes in as plus I omega L. The C comes in as minus I over omega C. So these two combine to get the imaginary part. Yes?
In that case, is the phase be zero?
At the resonance condition, the phase will be zero. Because you've already gotten one ahead. You've said that the impedance becomes minimum omega L equals 1 over omega C. Okay? And then your second question is, does that mean the phase has gone to zero? Because the inverse tangent of 0 over R is the inverse tangent of 0, and the phase is 0, and you're exactly right. So, at resonance, the phase of the impedance is 0. And if you're off of resonance such that the inductor wins, the phase is plus 90. And if you're off resonance such that the capacitor wins, the phase is minus 90. And under this condition, the inductor and capacitor exactly balance out each other's tendencies, leaving the whole circuit acting just like a resistor. So the phase becomes 0. Okay, so now, how is this going to help me answer that bottom question? What L would I use? What L would I use?
When that would cancel out the capacitor.
Yeah, so I take this formula, I bring the omega under. I'll have omega squared. How am I going to get omega squared? What's omega? 2 pi s. And what do I get for that? Because if I solve this for L, I have to bring that omega from the left to get this L. So what do I get?
3.38 times 10 to the negative 5.
3.3 E minus 5?
Yeah.
Yeah.
3.38.
Yeah, okay. What?
Henry?
Henry's. Henry? Yes.
Before we move on, could you please explain the high pass, low pass?
Yeah, I'd appreciate that too.
I previously had a table that looked like this. Okay? And in this table, I had a Z for each one of these. For the resistor, it's R. For the inductor, it's omega L e to the I pi over 2, Euler's happy again. And for a capacitor, it's e to the minus. Everybody agree with this? Now I'm going to make another column. I'm going to ask for infinity when. When does this formula go to infinity? What frequency would cause R to go to infinity? Never does. So there is no infinity when for the resistor. It's whatever it is, period. However, there is a frequency at which the impedance of the inductor goes to infinity. And this is for frequency goes where?
Infinity.
And there is a frequency when the impedance of the capacitor goes to infinity. This is when frequency goes up, what?
Zero. Yeah.
If you ask what each piece of this circuit tries to take for itself, the capacitor takes low frequencies. Because when you've got the infinity for your impedance, no one else can compete with you. You get it all. All the voltage comes to you when your impedance is infinity. So what does the inductor take for itself?
Higher.
And what does the resistor take for itself? Now, if you are a secondary circuit wired in parallel with one of these devices, it's like you've become part of that device's community because you share their voltage. So, if you wire yourself in parallel with the capacitor, since the capacitor is taking the low frequencies, that's what you get. And so the low frequencies will be passed on to you by the nature of the capacitor. However, if you are a secondary circuit and you wire yourself in parallel with the inductor, then in that case, you get whatever the inductor took because you have the same voltage that it does, in which case the high frequencies are passed on to you. And if you're the resistor, you get leftovers. So in an RC circuit, the leftovers are high frequencies. In an RL circuit, the leftovers are low frequencies. And in an RLC circuit, the leftovers are the resonant frequencies. Because the inductor takes the highest, the capacitor